All right, let's start into chapter 2 here, ladies and gentlemen. It's reviewing a lot of the chemistry kind of stuff that you guys went through last year. So, section 1, it starts off with the scientific theory. Okay, and so scientific method starts with asking a question. And so we ask a question. All scientific investigations begin with that. We do some experiments, we collect some data. Now, when we do this, when we do this step right here, we can do one of two things. We can either look at what's happening in nature on its own, or we can actually formulate some hypotheses and then actually run some experiments. If we do that process, revise and rerun over time, we end up with a scientific theory. Scientific theories are widely tested. Not one person does it. Multiple people from multiple different countries, organizations, all run similar types tests to come up with the same kind of conclusions. So it's supported by extensive evidence. If something's a scientific theory, it's not done on a whim. It's done over 50, 60, 70, 80 years of data collection and analysis. And as a result, most all scientific theories are accepted by the vast majority of scientists. Well, they're all accepted by the vast majority of scientists in a particular area. So if it's a physics concept, it's within physics. If it's an environmental concept, it's within the environmental scientific community that it's widely accepted. So scientific theories are something that is well established, lots of data collection, lots of evidence to support it, and almost universally accepted within the community. If you do something that is only pertaining to watching or seeing patterns of data that exist kind of naturally, we end up with scientific laws. So scientific laws aren't something that we've tested a bunch. We're just kind of observing and seeing those in action. And when we see those things happen repeatedly within nature, we create a law over that. Okay? Scientific theories and laws start off as results. Okay? So the data is collected. We have results that we have here at the top. Those results are put together into a scientific paper. Okay? The scientific paper then goes out for peer review. If it goes out to peer review and the experts in the field, the area, find there to be flaws in it, that paper then gets rejected and then gets recycled back into the process over again. If the paper is accepted, it works its way down this chain and it becomes published in a scientific journal. That journal then goes out to everyone in the scientific community for overall evaluation by people within the arena. When we work in the scientific community, when we work within the scientific community, it's really important that we get things that are peer reviewed. Okay? Peer reviewing things is essential for science. We want lots of people to get their eyes on it. We want lots of people to see it. We want lots of people to investigate whether it's true or not. Okay? And so scientific theory, scientists look over all this, analyze all this stuff in attempts to see if the science holds up. If it holds up and we see a different theory taking over, we call that a paradigm shift. And there's been many paradigm shifts over the years when it comes to science. Historically, there's been ones like heliocentric versus geocentric universes where we thought the Earth was in the center and we moved to a theory that the sun was in the center, and now we've progressed to where we are. The theory of how things came to be on the planet with evolution has taken a big paradigm shift. Recently, we've looked into plate tectonics and created some new ideas within that framework. That's one of the newer ones we have. And when that big shift takes place, that's referred to as a paradigm shift. Okay, on to section 2. Section 2 is your review of chemistry stuff. And so, if you recall from chemistry, elements are our starting blocks, our building blocks of this whole world of matter around us. Okay? Elements are an atom made up of protons, neutrons, and electrons that have the same makeup. They have the same number of protons in them, the same number of neutrons in them, the same number of electrons in them consistently. And that's basically the simplest form that an atom can take, that simplest form of matter that can retain its properties. If I take several of those elements and I throw them together, I create compounds, which basically two or more elements present. There's examples down here like water, nitrogen dioxide, carbon dioxide, nitrous oxide. These are examples of compounds that are used within the world, the universe. When it comes to the arena of environmental science, we need to focus on elements and compounds, of course, but a lot of times we spend a lot of time talking about organic compounds. The reason why we talk about them is because they're the building blocks of us. So anything that has a framework that's related to carbon, if the carbon is the main element present in it, it's an organic compound. Organic compounds make up the vast majority of compounds on the planet. All the other ones, which is a very slim number in comparison, are inorganic, meaning they don't have carbon present. Okay, but we're made of organic compounds. We're made of lots of different kinds of hydrocarbons, and hydrocarbons are very simply something that contain hydrogen, hydro, and carbon. And so there's lots of different versions of those, but they are essential to life on this planet. When it comes to a little more complicated structures, we have hydrocarbons, but then we'll add chlorination onto those. We add chlorine in. And when we do that, we derive a lot of other things, like, for instance, DDT that we talked about the other day in class. DDT is a chlorinated hydrocarbon. Chlorinated hydrocarbons a lot of the times can be toxic to humans, and so it's important for us to pay attention to those particular compounds. And then we have the simplest of hydrocarbons, the most basic building blocks you learned about in biology a couple years ago. Glucose is a fundamental one that's created by plants, right? It's one of the basic sugars out there, and so there's lots of simple carbohydrates that are built. But the idea that you need to know here is carbohydrates are made of carbon, hydrogen, and oxygen. And so they're hydrocarbons with oxygen attached to them. And so when we're talking about atoms and elements and how they're all interacting with one another, there's one law that is king, one law that kind of governs how all matter on the planet works, the law of conservation of energy. It's a law that you should know inside and out. Law of conservation of matter. Matter cannot be created nor destroyed. It can only be changed in form. So we'll have chemical changes and physical changes. Chemical changes being creating of new chemicals. Physical changes being it's the same chemicals, but like I melt ice, for instance, and so it changes its state. Those are going to happen. We're going to see different things show up there, but the amount of stuff it's made of, the amount of atoms it's made of, those are a constant, and so that law governs the whole process.